Let us start with our next lecture, and that is a follow-up of our discussion about random variables. Um, we discussed two random variables so far: the Dirac random variable, which is actually a deterministic variable, and the Bernoulli random variable. Um, Before we move on to other random variables, let us see something very interesting about the Everson bracket. So we have seen two different usages of the Everson bracket. On one hand, this appeared because we know it gives 1 or 0 depending on whether a condition is true or false. We saw how it is helping us to write a compact expression for the Dirac distribution. Yeah? So the Dirac distribution located at A is easily expressible in terms of the Everson bracket. But the same Everson bracket was also used when we tried to define the Bernoulli random variable. Yeah? So the Bernoulli random variable x will assign 1 if that condition is true, otherwise it will assign 0. So now you see two Everson brackets but entirely different meaning. Yeah? On the right you have one interpretation, which is that of a probability measure, because you know Dirac is a measure. It's a set function. Basically, you can say that on the right side you have a set function. On the left side, the Everson bracket is interpreted as a point function, because a random variable, in this case the Bernoulli random variable, is a point function. So do not get confused by the fact that they are both Everson brackets, because this Everson bracket and this Everson bracket gives you something. They both give you a 1 or a 0, but one is viewed as a function of omega, which is a point, and one is viewed as a function of b, which is a set. Now you know a set function and a point function, they are very different. A set function, so an example of a set function is a probability measure, and in this case you have the Dirac measure. And an example of a point function is a random variable, in this case the Bernoulli random variable. Now we will need both of these contexts. So here is one thing which is a little unfortunate. Here we have a dedicated symbol for this usage of the Everson bracket, because we know we will use delta A only for one purpose, and that is the Dirac distribution. We don't want to use delta A for any other purpose, because it would be a messed up situation. But we cannot promise that we will use X only for this purpose. Yeah, because here X is just a coincidence that we have used X to denote the Bernoulli random variable, but X can be used for any random variable. So we need a symbol that is dedicated to mean only this thing. So if I want to view this Everson bracket as a function of omega or any point, I need a new symbol and maybe a new name for this. And that brings us to a new definition, and that is the indicator function. So let me tell you why we call it an indicator function. Because this Everson bracket, this usage of the Everson bracket, only answers one question, and that question is whether the outcome belongs to A or not. So you have observed an outcome, and this function helps you whether A has occurred or not. So it's an indicator function, or you can say it's an indicator of the event A. So we will use this notation 1A of omega, because 1A is a function and it applies to omega. So 1a of omega, and 1, remember, is the bold one, so not to be confused with the number. 1a of omega will give me 1 if a has occurred, otherwise it will give me a 0, which means that a has not occurred. Now, so to summarize, the Everson bracket, when viewed as a point, will be the indicator function, because now we have given it a name and a symbol. And when the same Everson bracket is viewed as a set function, when you focus on the set, not on the point, then you will see it as a set function or a probability measure. So imagine we had known this indicator function before we were defining the random variable, the Bernoulli random variable. Our definition would have been very simple, simply that x is 1a. So that was just a short note about the need for a point function. Now, we still have one problem with Bernoulli random variable or Bernoulli family of distributions. We assume that we will always use 0 and 1 as our two values. So we assign 1 to our success, the event A, and we assign 0 to the failure, the A complement. Now, there might be problems where it will be more appropriate to use other values than 0 and 1. So let's say we want to replace 0 and 1 with two values A and B, and to keep matters simple, we'll assume that A is smaller than B. So you kind of want to replace 0 with A and you want to replace 1 with B, assuming that B will always be greater than A. And let's say, now otherwise it is very similar to the Bernoulli random variable. It is different only in the values, because in the values it is assigning to A and A complement, but values are important, so we cannot use X. So let's say we use a different symbol Y. So now how do we define that? And we assume that we have the same event space, because our interest still lies in A, whether A occurs or not. But this time we want to encode that not by 0 and 1, but by A and B. So B will encode the occurrence of A, and A, small a, will encode the occurrence of A complement. So here is our definition. You should ignore this because this is an old typing. I have to fix this. So you only focus on this part, the right part. So our new random variable y can be defined by using our new indicator function. It has to assign small b to any point that belongs to A, and you see the indicator function is telling me exactly that, 1A of omega. We just saw it above. And our random variable y will assign small a to any point that belongs to A complement. So the indicator function has provided us a language of defining this new random variable. This was unfortunately my previous attempt, and it is not appropriate. I mean, mathematically it is correct, but it is not appropriate. You should see it this way, because it's not a measure, it's a random variable. You can also look at this from this perspective, that y will map all the points of event A to B and all the points of the event A complement to A, actually the set. Now we could follow the same procedure and we could come up with a probability distribution for y and so on, but we don't want to do that. We know this random variable must be connected to the actual Bernoulli random variable x. So we must use that to derive its distribution. So it must be possible to derive the distribution of y from the distribution of x. Now, how do we go about this? The first observation we make is the nature of the indicator function. Yeah? The indicator function must have this property. Why do I say that? A point omega, so you see this will give me the whole sample space, because A and A complement can cover the whole sample space. So think about this now. Any point A can either belong to A, and in that case this will give me a 1, or it can belong to A complement, and in that case this will give me a 1. But it is not possible that omega belongs to A as well as to A complement, because otherwise I'll get 1 plus 1 is equal to 2. No, it's not possible, because omega cannot belong to both. Only one of these will be a 1, the other must be a 0, so the total has to be equal to 1. Now, how does this help us? We know our x was basically 1a, the indicator function of A. So we can now do something interesting. Let's look carefully at this definition of y. Y is a linear combination of the two indicator function, 1a and 1a complement. Now, if we know that 1a and 1a complement must satisfy this equation, we can eliminate one of them by using this equation. So if I, let's say, solve this equation for 1a complement, it will become 1 minus 1a, and I can plug this value there, and now see the magic. I have reduced y to this. So 1a complement has been eliminated. So y of any point omega will now be a plus b minus a times 1a. And now we also know that 1a is in fact the Bernoulli random variable x. So I can replace that with x. So hey, we have obtained an expression for y in terms of x. So if I start with any point omega, if I know what value has x assigned to it, that would be x of omega. I just multiply that by b minus a, and then I add the result to a, and I will get the value of y. Now, just to make sure that you know what we are doing, let's see how any pair xy. So let's say if small x is a typical value of x, the random variable x, and small y is a typical value of the random variable y, what this equation tells you that small x and small y, because they are values of upper x and upper y, they cannot be chosen arbitrarily. They must respect this equation. You see, this equation is just that equation above, with uppercase replaced with small x and upper y replaced with small y. And just see how 0 and 1 are mapped. So if x is 0, we place 0 here. So 0 times b minus a is 0, and 0 plus a is a. So that is what we expected. 0 corresponds to a. And if x is 1, then b minus a plus is b, so 1 corresponds to b. So this also means that we are going along the right track. So here we have actually discovered a new concept. What we have discovered is that we can start with any random variable x, and we can define a new random variable in such a way that values assigned by x are transformed by a function, let's call it g, and you see it's a point function from real to real. And similar to this equation, because we can have other problems like that, and we will have a different relationship between x and y. So let's call that relationship g. G will be a function. So values of x will be transformed to values of y by a function g, point function g, and we call that a transformation. To see it more clearly, the value assigned to any point omega by the new random variable y is simply obtained in two steps. You first assign a value to that point by x, so you just find out what has x assigned to it, and then you take that value, remember the value, not the random variable, the value, and then you apply the transformation g to that. And if you can recall mathematics, school mathematics, this applying one function on top of another function can be represented by the function composition g of x. This little circuit is off. So what this means is that first you apply x to omega, and then you apply g to the result of that. So it is also important to remember that this function g is not to be viewed, of course we will, for simplicity, we don't want to write this omega every time, yeah, because we know it will be there. So for simplicity you can write this transformation as uppercase equals g of upper x. But this is only for convenience. It is not to be seen as a function of x. You see, what that would mean is that you have a function that takes random variables and gives you random variables. Now, that will require you a very complicated definition. Here, this R is the domain of G, which means that it takes real values. It doesn't take real functions. Yeah, it doesn't take random variables, but it takes real numbers. So those are only values of random variables. Similarly, it returns real numbers. It does not return real functions. So if some mathematical object which takes functions, yeah, or random variables and returns functions, that must be very complicated. It does exist in mathematics, but we don't want to go into that. We'll return to that later on. So at the moment, this transformation, of which this was an example, has to be seen as a very simple thing which takes values of x and returns values of y. It doesn't take the random variable itself, but its values. So in our case, this transformation can be written in the form of a simple equation. We remove the omega to keep it simple, and we can also write it that way if we want to use the indicator function. Now, if you look at our probability measure, you remember that our probability measure for the Bernoulli random variable was a weighted sum of two Dirac measures. One look at it at 0, one look at it at 1. If we follow that reasoning, we don't need to prove that again, because we have everything ready. We know the actual probabilities will not change. So 0 has been mapped to 1 by our transformation G, yeah? And that 1 has been mapped to B. The probabilities must not change, yeah, because the original probabilities correspond to the event A and the event A complement, yeah. So our new measure for probability in the language of the random variable y will simply be an extension of that equation. 1 minus p doesn't change, p doesn't change. Only Dirac measure at 0 now changes to Dirac measure at A, because now it will be located at A. And Dirac measure at 1 is changed or transformed to the Dirac measure at B. Now, we have in fact discovered a distribution which we can call a two-point distribution. We cannot call it a Bernoulli distribution because part of the definition is 0 and 1 and we are using A and B. So we can call it, actually it's a standard name, two-point distribution. Just like you use two-state system in engineering. So two-point distribution in probability theory. And let's see something interesting here. We're not yet done. We have only expressed the probability measure in terms of two Dirac measures. We want to know the probability density function, the cumulative density distribution function, and so on. So if you look at this, if I want the discrete density of y, how will it go? I have to assign probability to such an event. Y takes a value k. Now this event can be written in this form. Remember what I have done, I have simply replaced y with the transformation a plus, you see, we see it there, yeah? So the same question asked by replacing y with its expression. Now if I solve this for x, yeah, I get this. Now this is a question about x, and I know how to answer that because I know the PDF of x, yeah? So what do? I can now have full characterization of y. The set of values is a and b as before. The strictly positive discrete density is this one. Why? Because an uppercase y taking value k is the same as the random variable x taking value this k minus a or b minus a. So I just apply the density of x to this value. Normally I would write small k there, but this time I have to write this expression. You see, that exact same expression appears here. Now let's go for the CDF or cumulative distribution function. That's not so straightforward, but we can still go about it. A question for CDF will look like that. Uppercase y taking a value not exceeding k, we simply replace y with the expression under the transformation, and we now solve this inequality. We solve this inequality. So take that a to the other side, you get k minus a, and then you divide by b minus a, divide by b minus a. Now you will realize why I had to assume in the beginning that b must be greater than a, because then this will be positive. Because if b is not greater than a, this will be negative, and then this inequality has to change. We don't want that complication. If b is not greater than a, I have to relabel it, and I'll have to label it because these are just symbols. So I will use labels. Yeah, I mean, there are mathematical ways of dealing with that, but I don't want to go into mathematics. After all, this is a course of probability, not mathematics. We can get to that in some other lecture. So I can now Right. If you look at this now, the question for CDF of y looks like that. The question of the same question for x will take this form. So small k will be replaced with that expression. You see, and this less than or equal to doesn't change. So the CDF of y at k will be the CDF of xk, the CDF of x at that thing. You see. Remember, these are not the actual PDF and CDF. The actual PDF CDF can be recovered in this way, and that is something which you already know. So let's stop here, and the second part of this lecture, I'll not rename this. This will still be called lecture 17. So you can think of this as an interval in lecture 17, and I'll post that video either today or tomorrow. So stay tuned and stay healthy.